Okay, now let's consider IC number 74163. This IC is a synchronous 4-bit binary counter. Okay. The table function is for this. And okay, and the pin, okay, layout. This is clock, clear, load, enable P and enable T, data input D, C, B, A, and output QD, QC, QB, QA, and RCO, ribbon carry output. Okay, now let's consider the internal circuit of this IC. How this circuit work? Okay, let's follow this table function. At first, if clear active, okay, clear active low node, and this terminal is active flow, okay, indicated by this inversion bubble. When clear active, namely when you apply logic 0 at this terminal, it will make the output QD, QC, QB, QA become 0. Okay, let's consider how does it work. Okay. This is clear. When clear is 0, okay, this is inverter, right? Its output become 1. Okay, 1 at here, 1 at here, and because this body is AND, right? AND function, but input active low. So when this input is not active, right? Because it's 1, okay, but this is active low. That means output will be not active also. This one also output is not active. Output is active high, right? So input now then become 0 because it's not active. This one also not active, so the value of this signal is 0. Then that means this input is 0, output of this AND gate also 0. And for this is 0, output is 0. 0, 0, all together, the output of this OR gate is 0. That means when you apply 0 at clear, the value of 0, okay, will feed to input of D flip-flop. Okay, this one also, and this one also. 0, 0, 0. Okay, will be applied into input of D flip-flop. Then when clock tick, okay, when clock tick, 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 flip-flop will read data from its input. Then because data is 0, 0, 0, 0, so the output then update to 0, 0, 0, and 0. So this is clear, okay, clear function. Note the output when you apply clear 0 at clear, the output not become 0 suddenly, but it wait for clock tick. Okay, this kind of clear is called synchronous clear. Okay, synchronous with clock. Okay, next function is load. Okay, if clear not active, one and load active. XX mean it is unspecified. It can be 0 or 1. 0 or 1. Okay, you give the same result. Okay, So we write X, okay, unspecified, like don't care, okay. Thus this load is 0 and clear not active is 1. The result is what? And the flip-flop, the output of the flip-flop will be the value of input DCBA. That means if you apply 1 at clear, now clear not active, and make load active, apply 0 at here. When clock tick, this counter will read data from DCBA to update QD, QC, QB, and QA. Okay, this behavior is called load. Okay, load. Okay, load is read data. Okay, multiple bit to update at the output at the same time. Okay, now let's consider when clear is 1, right? Row is 0. This one is active. The inverter output now is what? Output of this is 0, right? This is active low, so this is active. This output is 1. 1 at here. This is not active, so output not active. So output now is 0. This is 1, right? 1 and what? And A. So this output is A. And this is 0. This output also 0. A also is A. That means now, okay, X not input, data input from A, okay, flow and feed to D. Okay, this one also B, data B, you feed to D flip-flop. C also, and input D also. You feed to input of D flip-flop. So that means when clock tick, each flip-flop will read its input data and update. Okay, you see A, you see B, C, and D, right? So output will update to A, B, C, D, or load. Okay, this one is called load, and data will load and update data when clock tick. So it's synchronous load. Okay. Synchronous load. Okay, and now if not clear, not load, and enable is not active, what happened? If enable P, enable T not active, that means it's 0, 0, this output will be 0. And if clear and load not active, 1, 1, right? So what happened? This output not active, so output now is 0. 1 at here, 0 at here. So that means this output is 1. Then 1 at here, this is 0, right? 0 at here, so this output of AND gate is also 0. And let's consider this is 1 and something from XOR. This XOR. Let's consider this one. This Q active flow output of QA, right? So this point is QA prime, but this is invert. So you can consider it is cancelled together. So you can consider like QA connect directly to XOR gate without any inversion bubble. That means this output is something XOR QA. Something XOR QA. Now Now something is what? Is the result between enable P and enable T. If enable P, enable T, one of them is 0. Okay, output is 0. So what happens is become 0 XOR something, right? 0 XOR QA, then the result is QA. That means now QA is fed into its input. Okay, so this one also QB fed to input of the flip-flop of QB. Okay. This one also QC. Okay, feed to this one, and QD also feed to this one. So that means when clock tick, all flip-flop will update the data with the value of QA, QB, QC, QD, okay, respectively. Okay, so we update by itself, so nothing changed. So this is hold mode. That means the value is still be the same for the previous one. Nothing changed. It's hold. Okay. Hold mode. So for counting mode, enable P, enable T must be 1, 1, both. So this is 1, 1. If this is 1, 1, it's 1 at here. So when this is 1, this is 1, right? And for example, this is QA, right? So QA XOR 1, then it's become QA prime or toggle. So the toggle value of QA then feed to input of D flip-flop. Then when clock tick, okay, QA will be updated with opposite value, okay, of itself. So it's toggle. QA is LSB, right? For LSB, it will toggle for every clock tick. Change 1 to 0, 0 to 1 for every clock tick. But for QB, how about QB? Okay, when enable P, enable T is 1, 1. Output of this AND is 1. Okay, so the toggle will be occur when what? When this output of AND gate is 1, right? Now enable is 1, right? And how about this? This come from QA, right? Invert of QA, then invert. So it's QA here. So if QA is 1, 1, 1 and 1 is 1. So toggle occur. So it will update with opposite value of QB. And QC, QD also. For example, when QD is toggle, right? QD XOR with something. Toggle will occur. Okay? QD when this is 1, right? So when this output of AND gate is 1, when enable PT is 1 both, right? And output of this AND gate is 1. When it's from what? From QC, from QB, and from QA. That means if QC, QB, QA is 1, 1, 1, okay, the previous digit is 1, 1, 1, okay, the toggle will be occur, okay, for QD. So when clock tick, okay, we will update with QD prime. So it's counting mode. Okay, and the last output is RCO, return carry out. RCO will be 1 when what? When enable T is active. Okay. And QD, QC, QB, QA all is 1, 1, 1. Okay, the last value of the counting. So RCO, you can use this as indicator that now the state is the last state of binary counting. Okay, for card is 1, 1, 1, 1 for 4-bit counting. Okay, now let's see how to apply this 163 counter, okay, binary counter. For the simple one is free running counter. Okay, you just connect, okay, clock directly to clock signal, low high, low high, low high, and clear. You don't know what clear, you want what load, right? So connect to logic high or 5 volt and make enable P and T active both. That's all. So for every clock tick, positive edge. For every clock tick, the result is make counting mode, right? Because enable P and T is 1, 1 and not clear, not low. So the value will increase by 1 for every clock tick, like this. For example, if start from 0, 0, 0, 2, okay, one thing you should be careful. MSB is at QD. QD is MSB. QA is LSB. Okay, let's start from this. This is MSB. Okay, QD 0, 0 when clock tick, positive edge. So it becomes 0, 0, 0, 1. When clock tick, change state to 0, 0, 1, 0. When clock tick, okay, change to 0, 0, 1, 1. And so on until 1, 1, 1, 1. When it's become 1, 1, 1, RCO will be active. Okay. Okay. And this is 4-bit binary counter. Count from 0, 0 to 1, 1, 1. When clock tick again, it back to 0, 0, 0, 0 state again. Okay. And please take a note for the clock frequency and LSB bit frequency. The frequency of LSB is half of clock frequency, right? It's 1 period, right? 2 period of clock, 1 period of LSB QA. So the frequency of QA is half of clock, and frequency of QB is 1 period of QB equal to 2 period of QA. So QB is half, its frequency is half of QA. That means frequency of QB is 1/4 of clock frequency, right? Okay. QC, okay, is half of QB, so it's 1/8, okay, of clock frequency. Frequency of QC 1/8 of clock frequency, okay, and so on. So you can apply this as frequency divider, okay, to divide by 2, 4, 8, 16, okay, for example. Okay, and if you want to make, for example, 3-bit counting to count 0, 0, 0 to 1, 1, 1, you can also use this IC. Just use these 3 bits. It's okay. Why? Because if you consider the sequence of binary counting, let's back to this one. This one. Okay. For 4 bit, you count from 00 to 111, right? But if you consider 3 bit, that's 3 bit, then it becomes 00 to 111, 0 to 7 in decimal, and after that it will repeat, okay, 000 to 111 again, so it's repeat, okay, again. So you can use this 3 bit, okay, if you want to count 0 to 7. So if you want to use 2-bit counting, so you use just Q, B, and QA. That's all. This is for free running counter. Free running means no any condition, just run or count, okay, for the normal counting. Okay, and this another, okay, counting counter. For example, I see number 160, 161, 162, 169. Okay, for 160, this is model 10 counter. That means if you count 0 to 9, or 0, 0, 0, 0 to 1, 0, 0, 1 in binary. And this one is asynchronous clear. Asynchronous clear when you it's clear, it will clear suddenly. And for this is 161 is 16 counter. It's count 0 to 15. Clear. And for this one is modulo 10 counter, count 0 to 9 and synchronous clear. And 163, okay, you already know. 169. For this one is up down counter. Is control input up down. If this is 1, it will count up. If it's 0, it's count down mode. And for RCO, for this is active flow. RCO will be active if it's count to the last state. That means if you use count up, RCO will be active. Mean RCO will be 0 when QD, QC, QBK is 111. But for countdown, when you apply 0 here, RCO will be active or become 0 when QD, QC, QBK is 0, 0, 0, or the last state. The last state of countdown mode. This one is just show some example of timing diagram for count from 0, from 0, 0, 0, 0 to 1, 0, 0, 1. And RCO will be active here when we count to the last state 1, 0, 0, 1. Okay. This is for model 10 counter. Okay, now if I want to count from 5 to 15 by using this 163 counter. What should I do? Okay, I want to count from 5 to 15. 15 is 1, 1, 1, 1, right? So when it becomes 1, 1, 1, 1, RCO will be active. So we can use this RCO signal, okay, to load. Load what? Because when I want to count 5, 6 until 15, right? When 15, when clock tick, you back to 5 again. If you do nothing as free running for 15, you back to what? To 0, right? But for this example, I want to start at 5. That means when 15, when clock tick, you go to 5. 5 is 0, 1, 0, 1. So I will use load. And because load active load, so I add inverter here. That means when ASU active, load active, then I apply 0, 1, 0, 1 at DCBA. That means when clock tick, right? When clock tick, load active. So this IC will read data from DCBA or 0101, okay, to update DFIFOP QD, QC, QB, and QA. So the counter can continue, okay, 15 to 5 state. And then when it becomes 5, now RCO is not active, right? Because 5, state 5 is 0, 1, 0, 1, okay? QD, QC, QB, QA not all 1, 1, 1, okay? So RCO is not active. That means load is not active also. So now because enable P, enable T still be 1, 1, so it's counting mode. That means when clock tick will increase, okay, by 1. So when clock tick, the next value is 0, 1, 1, 0. When clock tick again, it becomes 0, 1, 1, 1. Okay, when clock tick, for the next clock tick is 1, 0, 0, and so on. Okay, until 1, 1, 1, 1. Right, until active again, and then change to load mode, and then if you load 0, 1, 0, 1. Okay, again. So you can repeat this one. Okay, and for the next example, I want to count from 0 to 10. Okay, what should I do? Okay, you can do something like this, right? For 0 to 10, that means it's a 0 when clock tick, change to 1, clock tick change to 2, and so on, right? Until 10. When it becomes 10, when clock tick, now I want back to 0. Okay, not continue to 11 and so on. Okay, I want to count up to 10 and then back to 0 again. So that means you must check that now it's become state of 10 or not. If yes, you may clear. Okay, clear. So how to check is 10? And in binary, 10 is what? Is 1, 0, 1, 0, right? Right? So you can check by using this condition 1, 0, 1, 0. So you can use logic gate to check something like this. Okay. 1, 0, inverter, right? 1 and 0, active flow or inverter. Okay, to make this AND gate, okay, active. Its input must be 1, 0, 1, 0. So it's active high, active low, or invert. active high and active low. Anyway, because you use count-up mode, that means the value, back to this one, sorry. Okay. If we want to take state of 10 or 1010, if you count up from 0 to 10, actually you need not to check all 4 bits. You can take only 2 bits of 1 1. That's enough. Okay, because no any period state that have 1 at here and 1 at here, right? No. So you can check 2 bits. Okay, it's enough to confirm that now it's state of 10. So this example, so we just take 1 at here, 1 at here. That's enough. When it's 1 1, this output active, and because we want to connect to clear, and clear is active flow, so we must use active flow output also. That means when it's called to 1 0 1 0, this output will be 0 or active. Then it make clear active, and output is not active study for this IC is synchronous clear, so it's wait for clock tick. When clock tick clear active, so the output will be 0 0 0 0. Okay. After that, when this bit is 0 0 0, it's not 1 1, right? So this output is not active. It's become 1. Now clear is 1, and enable connect to 5411. Okay. So now it become counting mode. That means when clock tick, then it change to 0 0 1. If clock tick again, it becomes 0 0 1 0, and so on until it's become 1 0 1 0. Okay. State of 10 again to make this output active and then clear. If you want, if you don't want to use clear, actually you can use load instead. That means you just connect this one to load. But if you load, you must apply 0 0 0 0 at here, okay, to load the value of the CBA or 0 0, okay, to update the value of QD, QC, QB, QA for the next state. Okay, and next example. And now if you want to count from 3 to 12, now what should I do? 3 4 5 6 7 8 9 10 11 and then 12. The same idea, right? Let's check if 12 or not. 12 is 1 1 0 0. If yes, load, right? Load what? Load the next value of 3, right? 0 0 1 1. So for this one is easy, right? So it check 1 1 at here, right? For state of 12. And I want to use load, and because load is active flow, so I add invert at the output to make it active flow. So when it's count to 1 1 0 0, this signal active, or it's become load mode or load function. So for load, we read data from the CBA, right? And now I want the next state is 0 0 1 1. So I connect 0 0, okay, to ground, and 1 1 connect to 5 4. That's all. Okay. And another example. What happens if I want to count with this sequence 0 1 2 3 4 7 7, 8, 9, and then back to 0 again. What should you do? Yes. Okay, for the state that just one increment, okay, you can use counting mode, right? Do nothing, right? And just make enable P, enable T is 1, 1. But how about this one? 4 to 7 is not one increment, right? So what should you do? Maybe you must use load, okay? By checking that now it state of 4 or not, 0, 1, 0, 0 or not. If yes, load the next value to 0, 1, 1, 1 or 7. Okay. After that, it is counting mode. And then when it becomes 9, you want the next day is 0, right? You may use clear. Okay. Check 9 or not. 1, 0, 0, 1 or not. If yes, okay, let's clear. Oh. This case, you must check 4 and check 4 to load and check 9 to clear. How to check 4? 4 is 0, 1, 0, 0, right? Can you check only the digit is 1? No, you cannot, right? Because you use another step that greater than 4. That maybe this bit is 1. For example, 7, right? 7 is 0, 1, 1, 0. For 4 is 0, 1, 0, 0. If you use only this bit, it's not enough because 7, this bit also 1. So you may use more than one bit. Maybe use this bit and this bit. So to make sure that I check 7, 8, and 9. So if you use 1 at here and 0 at here, maybe not enough, right? To make sure that it's set of 4. Okay, so you use this bit is 1 and this bit is 0. Check. Active low at here, active high at here. Okay, to load. Active low to load. And the next state is 7. So you apply 0, 1, 1, 1 for DCBA. And check 9. 9, okay, 9 is just check 1 at here, 1 at here. And check 1 at here. And use clear. Okay. And what happened if I want to count from 1, not from 0? That means I want to count 1, 2, 3, 4, 7, 8, 9, and back to 1. Okay, what should I do? Okay, 1, 2, 3, 4, 7, 8, 9, and then back to 1 again. Okay, so from the previous example, I just take it's 4 or not. If yes, let's load, right? Load 7 for the next step. Now 9 for the previous one is 0, right? You can just clear, but this one you want 1, so you must use what? Check 9 state and then load, right? And the next state of 9 for 9 is 1. Okay, that means you must use load, okay, for state of 4 and or state of 9. So you just check, right? For 4 you just check this bit is 1, this bit is 0, right? Active flow. You check 4. If yes, this output will be 1. And check 9, right? 9 is 101, so check this bit, right? It's 1 and this bit is 1. This test or this state, okay, we use load, so you this or this all together and go to load. But load is active load, so I add a virtual bubble at here and connect to load. Now the problem is the value of DCBA. Now it's not constant. It's not constant. For state of 4, if QD, QC, QB, QA, right? This is 4, so it's 0, 1, 0, 0. The next state you want 7, right? 0, 1, 1, 1. That means the value of QD, QC, QB, QA must be DCBA must be 0, 1, 1, 1. But for state 9, 9 is what? 9 is 1, 0, 0, 1. The next state you want 0, 0, 0, 1, right? Okay. So from this one, that means input D is constant 0. Input A is constant 1. So you can connect 0, okay, for D and connect A to logic 1. How about CB? CB is 1, 0, right? 1, 0. Oh, it's the same as this bit, right? QC. So you can connect, okay, QC to C and B. That's all. And if you want to count not 4-bit, this IC, okay, is support for 4-bit binary counting. But if you want to count more than 4-bit, for example, you want to count 8-bit, you can use two IC of 163 connect like this, namely use the same clock, okay, same clear signal and same load signal, and enable, counting enable. And for this enable, it's from RCO. Okay, that's all. Okay, for example, if counting enable is 1, it's 1. So enable P, enable T is 1, 1 now. And if not clear, not load, pi 1, 1. Okay, so now it's counting mode. If I start from state of 0, 0, 0, 0, 0, 0, 0, MSB is at here, MSB, and this is LSB. Okay. So when clock tick, it count up, right? Then it's the next value is what? Is 0, 0, 0, 1. And because the previous state is 0, 0, so RCO is not active. RCO connect to enable PT, right? So enable PT is not active also. That means even clock tick, when clock tick, nothing changed for this IC. So this is to be state of 0, 0, 0, 0. So when you consider 8-bit, the result is from 0, 0, 0, 0, 0, 0, 0, 0, 2, 0, 0, 0, 0, 0, 0, 1. And when clock tick again, then it's become 0, 0, 0, 0, 0, 0, 1, 0. When clock for the next clock tick, nothing changed at here, 0, 0, 0, 0. And then this one count up to 0, 0, 1, 1. Okay, until go to the state of 0, 0, 0, 0, and 1, 1, 1, 1. Now it's 1, 1, 1 for this. So R0 then become active. Now enable active. So when clock tick, this IC change to 0, 0, 0, 1, and this one, okay, change from 1, 1, 1 to 0, 0, 0, 0. So this to show you, okay, how does it work for 8-bit counting by combine these two IC together, okay, by using RCO of this IC to be enable input for the next IC. Okay, and for this one, just show you some example. Okay, to count from 63 to 255. Okay, actually it's similar to the previous example. Okay, by using RCO, connect to enable for the next IC. And because 255 is 11111111, right? So you can use this RCO, okay, to check that it's become maximum counting value or not. And for the example, there's more condition. Okay, if it's become max count, okay, so this bit is become 1. It's become 1, and this is OR gate with active low input. If this is 1, right? And if goal is to be 1, that means this output is not active. It becomes 0. So enable is not active. It's not active. So counting will be stop. Right? We stop at the value of 11111111 and wait until go active. That means change to 0. This bit active, so this output become 1, and make the circuit, okay, back to the counting mode again. That means make enable active again. Okay. Furthermore, this bit is when this is 1, 1, and this output connect to load. So now load active, right? Load active. So you load the next data, right? You want to, and the next value is 63, right? 60 is 0, 0, 1, 1, 1, 1, 1, 1. So it's connect 0, 0 at here, low, low, right? And 1, 1, 1, 1, 1, 1. Okay. Okay. And for this signal, okay, just want to reset, okay, to load, okay, 63 state, okay. Whenever you want, you just apply this. Okay, and next, show you some problem that may occur, that may be occur if you use decoder. Okay, one 3, 8. To decode this binary output from counter 163. So remember for decoder, for example, if for the state 0, 0, 0, CBA, right? Y 0 is active, okay, become 0. Another bit is not active, it's 1, 1, 1, because output of this as is active low. Okay, and when clock tick, right, it's in state 002, 001, right? So CPA of this decoder then is 1, so Y1 active becomes 0, and the is 111. When clock tick, change to next state 010, right? Y2. So Y2 must be active, right? And the is not active, something like this. So the problem is if you change state from state of 00 to 001, actually this one is not any problem. But if you change from 001 to 010, it's problem. If that is 2-bit change, 0 to 1, 1 to 0. If this 2-bit change with different rate, I mean, if this bit change faster, what happened? Change 0, 0, 1, try to change to 0, 1, 0, right? But if this bit change faster, that means it will become 0 before this bit become 1, right? So it becomes 0, 0 for a short period. That means Y0 will be active for a short period. So for example, for this one, state 1 change to state 2, so it make S0 active. But if change 0, 0, 1, try to change to 0, 1, 0, and this bit change faster, that means we go to 1, okay, before this bit change from 1 to 0. So now you can see it's state of 0, 1, 1 for a short period, or S3, right? Be active a little bit, this one or this one. So glitch occur. Okay, which may be occur to this one or this one, based on which bit is faster, okay, to change. So if you don't want glitch occur, what should you do? Actually, if you use decoder, the glitch maybe occur. Okay, maybe occur. So if you don't want to use this one, you may add D flip-flop, okay, for each bit. Namely, you use register. Okay. Register for this one is 8-bit register. Internal there is D flip-flop inside, right? So and use the same clock. So what happened? Because D flip-flop will update its value when clock tick, right? That means for this clock tick, it will read data at this point of time, which there is no any glitch. Okay, the glitch already gone before the next clock tick, right? Because glitch occur with a very short period, right? So you can solve this problem by adding more D flip-flop or register. Anyway, you might wait, okay, for the next clock tick. If we for you this one, that means it's one delay of clock for the final output. Okay, so that's all for today.